So we're starting today off with number 119, review. So it says the function f is defined as f of x is equal to x squared minus 1 times e to the x. All right, first it says A, and I guess before we get going on this, Megan, were there any particular parts of this question that you had questions about, or is it just the whole thing? Just the whole thing. All right, we'll just do the whole thing then. Okay, so part A says find the limit as x approaches negative infinity of f of x and the limit as x approaches positive infinity of f of x. Well, in order to do this, we need to know what the behavior of the graph is, okay? And so let's see, I'm going to look back at what I did just because it's been a while. All right, so in doing this problem, I tried direct substitution. So I said that this guy right here is the limit as x approaches negative infinity of, instead of f of x, we're going to write the actual function, x squared minus 1 times e to the x. And plugging in negative infinity would give me this. Negative infinity quantity squared minus 1 times e to the negative infinity power. Well, negative infinity squared, what kind of value, what will that give me? What will that give me? It'll give me a positive infinity, right? So this is, this is infinity minus 1. Well, that minus 1 is negligible because it's infinity so big that the minus 1 doesn't mean anything. So infinity minus 1 times e to the negative infinity. Well, instead of doing that, like writing that like that, I'm going to write it like this. E to the infinity power, but all that in the denominator. We can do that, right? With the negative exponent. Okay, so what this becomes is infinity over e to the power of infinity. Okay, now the final answer for this portion is 0. And here's why. Whenever we have a really, really big number in the denominator, that means 0. Even though we have a really, really big number in the numerator. Okay? Technically, the number in the denominator, it's e to the power of infinity. So it's technically a little bit bigger, but if you were to go on that route, then you talk about the square here. But here's what I want you to remember. If infinity is in the denominator, it's going to yield us some number over a really, really big number, which approaches 0. Okay, so that's why that answer is 0. Now for the other one, if we were to write this out as the limit as x approaches infinity of, instead of f of x, it's x squared minus 1 times e to the x, and let's plug in infinity. So we get infinity squared minus 1 times e to the power of infinity. Here it's not negative. So now infinity squared minus 1, well, that's just infinity, and then times e to the power of infinity, that's just going to be infinity. It's just going to be a big number. So this limit is infinity. Okay, does that help for part A? Questions, any clarification needed for part A? Or if you were in Boston, you'd say part A. You have the because that's how they say it. I don't know. Bostonian accents are pretty cool. So, Park the car and Harvard Yard. So, anybody ever been to Boston? Boston. They talk awesome. Yeah. So they're not known for being nice. Part B says find the critical numbers of f. in order to find the critical numbers, we need to find the derivative. So let's first find the derivative. F prime of x is equal to, because we have a product going on here, we're going to use the product rule. So I'm going to say the first, x squared minus 1, times the derivative of the second. The derivative of the second is e to the x times 1, because it's e to the x times the derivative of the exponent, which is just 1 in this case, plus the derivative of the first, which is 2x, times the second. That's the derivative of f of x. And now we'll just rewrite it though by factoring out an e to the x in both of them. They both have an e to the x, so we'll factor out e to the x. And if you factor e to the x out of the first factor, then you get x squared minus 1 is left. And then I guess I should really put brackets here. I'm going to put brackets and then parentheses. So that's what's left from the first factor, minus from the second factor we have just 2 to the x. Excuse me, just 2x, not 2 to the x. And then simplifying this in here, we get that it's e to the x times x squared minus 2x minus 1. Finding the critical numbers occur when f prime of x is equal to 0. So when the tangent line is horizontal, okay, that's when critical numbers occur. So we're going to take this and set it equal to 0. Okay. We take each factor from here and set it equal to 0. So that breaks into two equations. We have e to the x is equal to 0, and then we have this factor, x squared minus 2x minus 1 is equal to 0. Solve each of those equations to find the critical values. Okay, when will e to the x equal 0? Hunter? Back up.
X squared minus 1 plus 2x for the second step.
Right here? Right here?
Like we haven't taken out e to the x. Wouldn't it still be x squared
Yeah.
minus 1 plus?
Yeah. That should be a plus, so then that should be a plus. Good, good. Yep. That's what it should be. And then I also have, okay, cool, cool. So then down here it'd be a plus. Thank you. So then for this guy right here, if you were to take the natural log of both sides, the e in the natural log here will go away, and then you have x is equal to the natural log of 0. What's the natural log of 0? Undefined. So at this value, it's undefined. There is no critical numbers from this equation. Okay. So then we go over here and we solve this one. It'd be really nice if this factored, but it doesn't. So one of two ways. You could either do complete the square, or you could do quadratic formula in order to solve this one. For sake of time, I am going to, well, you guys pick. They're both the same amount of time. So Megan, since you picked the problem, do you want me to complete the square, or do you want me to quadratic formula? Sure. So in order to do that, we need to clear this spot. So I'm going to say that's x squared plus 2x blank is equal to, move that 1 over. Now we need to fill the spot with half of b squared. So what's half of b? What's half of 2? And then square it. So that's a 1. If I add a 1 here, I have to do the same thing over here. So then it becomes x plus 1 quantity squared is equal to 2. That's how this factors right here, x plus 1, x plus 1. And then take the square root of both sides. You get that x plus 1 is equal to plus or minus the square root of 2. And then get x by itself by subtracting 1. You get that x is equal to negative 1 plus or minus square root of 2. So these are our two critical numbers. Negative 1 minus root 2 and negative 1 plus root 2. So we are going to test on the intervals from negative infinity to, so this is part C. Okay, so we're going to figure out our test intervals. From negative infinity to -1 minus root 2, and then from -1 minus root 2 to -1 plus root 2, and then from -1 plus root 2 to positive infinity. We're just trying to get the entire domain there. We're going to test our intervals. Now, we figure out what the sign of f prime is on those intervals. So I like to plug in numbers. -1 minus root 2, just to get an estimate of what that would be. Root 2 is about 1.3-ish, so I'm going to say this is about 2. -1 minus 2 is -3. I know -3 is somewhere between this. So for my test value, I'm gonna use the value -3. I'm gonna plug that into my original derivative equation up here. Okay, so if I do the work for that, I say that it's going to be e to the e to the -3rd times -3 squared plus 2 times -3 minus 1. And then this right here is just going to be a fraction. That's going to be, all we're trying to do is trying to figure out what the sign is. This is 9, and that's -6, and that's -1. So 9 minus 6 is 3 minus 1 is 2. So it's going to be 2, positive 2, over e to the 3rd power, which would give us a positive value. So, for the first interval, f prime is positive. For the second interval, I'm just going to pick 0, because 0 is between here, and that's easy to plug in. So if I get, it's going to be e to the power of 0 times 0 squared plus 2 times 0 minus 1. Well, this is 0, that's 0, minus 1 is -1. E to the power of 0 is 1, so it's 1 times -1. That gives us a negative number. And then for this one, instead of trying -3, I'm going to try +3. And plug it in, it's e to the 3rd times 3 squared plus 2 times 3, and then minus 1. And that's going to give us 9 plus 6 is 15, minus 1 is 14, times a positive number. So 14 is positive times e to the 3rd, which is positive, will give us a positive value of f prime. Alright, so then, the sign here tells us when it's increasing or decreasing. So it's increasing on this interval. I'm going to say it's increasing. It's decreasing on this interval, and it's increasing on that interval. I'm not going to write it out. I wrote it out before, so you need to look at the notes online. Okay. Now, for the last part, which is step D, we need to find where the relative maximum and where the extrema are, the relative extrema. So whenever the sign of the derivative changes from positive to negative or vice versa, we have a relative extrema. In this case, it changes from positive to negative. So if I were to draw a picture, the slope is positive, and then the slope becomes negative. So we're going to have a maximum. And here, the slope is negative, and then it changes to positive. So we're going to have a minimum. So the maximum is at this x value, so -1 and -1 minus square root 2, comma, we need to know what the y value is. We don't know yet, but we do know that that's a maximum. And then this guy right here is a minimum, -1 plus square root 2. And we don't know the y value yet, but we know that this is a minimum. How do we find these y values? How do we find the y values for those points? Megan? Yes, plug them into the original. So you plug that guy back into the very original equation right here, and you will get your answers. And I'm just going to, well, off to the side, f of negative 1 minus root 2 is approximately 0.4318. And f of negative 1 plus root 2 is approximately negative 1.2536. So you could find that just by plugging it into the original function. So then that's what goes in here, 0.4318 and negative 1.2536. Cool. All right. Let's move on. We're going to begin section 3.4, and this is concavity and the second derivative test. So concavity and the second derivative test. Today we're going to deal mainly with concavity. So it's 16:29. We get out of here at what time do we get out of here? Cool. So we got 10 minutes. That's good. All right. I want you to draw a part of a flower. So there we have part of a flower. It's like, I don't know, science class, and you cut it in half and you only take half of it home. I don't know. But here we have part of a flower. And this petal right here is concave down because the slope is decreasing. So this is concave down, because the slope is getting smaller. Jimmy, what would the concavity of this guy be? Would it be concave down or concave up? Yep. So I'm going to say CU for concave up. Because the slope is increasing. The slope right here is a number, and the slope is right here is a bigger number. Okay? So the slope is increasing. Hunter, talk to us about the slope of this portion of the flower right here. Right. So we're not talking necessarily about steeper or shallower. We're talking about numerical value. So what's the slope? Give me an example of the slope right here. What's a number of that slope? Yeah, sure, negative 1/2. How about right here? What's the slope? It's steeper, right? So but still negative, right? So we'll say over here that this is negative 1/2, and this guy is negative something steeper. So give me a number. It doesn't necessarily matter, other than it's got to be steeper than this. 1/4 would be. So no, you can get it. So like this guy right here, we went down 1/2, right? How about this guy? We go down 2 over. So what would that slope be? Negative 2. Okay. So the absolute value is bigger, but that's not what we're looking at. We're actually looking at the number. So this slope is negative 1/2. This is negative 2. Which one's smaller? which one would you rather have in your bank account? Negative half a dollar or negative $2? Negative half, right? Because it's more. So this is smaller, so the slope is decreasing. It's going from negative 1/2 to negative 2. The slope is decreasing. So because the slope is decreasing, it's concave down. So this one would be CD. So let's get that in our notes. Okay, concave up. Concave up is when the slope is increasing. And concave down is when the slope is decreasing. So Alexis, what would the concavity of this other portion of the flower be? Yeah, it is, because the slope is increasing. So right here it might be negative 2, and over here it might be negative 1/2. So the slope is increasing, it's getting bigger. So it's concave up. Okay? Now, it'd be really nice if we could figure what that is without a graph. But before we do, let's well, yeah. Here's how you do it. Okay, so you're going to find the slope is increasing or decreasing. Yeah, let's do it by figuring out a by looking at this problem right here. F of x is equal to negative x cubed plus 6x squared minus 9x minus 1. This is number 3, by the way, for your homework tonight. First one. Okay. We're going to figure out the concavity of this guy. And that's when the slope is increasing or decreasing. So let's plug in, well, just to show you what this looks like, I want to, okay, for those of you who are watching this later, right now I'm going to desmos.com and I'm going to graph this function. So if I were you, I would go to Desmos real quickly and graph this. So f of x is equal to negative x cubed, and then plus 6x, and then that to be squared, and then minus 9x, and then minus 1. Okay, and we want to change that. We don't want to be in pi. We just want to be right there. And we want to examine the concavity of this function. So looking at this graph, right now the slope is increasing because it's getting because it's really a steep negative here, and then it's changing to a positive. So the slope is increasing right up until about here, and then the slope is still increasing. So right here the slope is still increasing until right about here, and then right here the slope starts to change from increasing, it starts decreasing, and then it decreases from here to infinity. Okay, so here's how, in fact, if you were to, let's graph this right here. Let's do the derivative, f prime of x. Here we have the slope. The slope is positive from this point to this point. The slope is positive from this point to this point. But the slope is, right here, it's positive. And let's see what else we're looking at. Oh, just for fun, let's do f double prime. See what that looks like. F double prime is a line. Okay, so in order to test for concavity without looking at a graph, which is the idea, because we want to, we don't want to have to graph all of these all the time, we need to find the second derivative. So let's first find the first derivative, and then from there we'll find the second derivative. And let's go with column. Give me the first derivative. Yep. Yep. Good. Alright, now let's find the second derivative. Mason, give me the second derivative.
Negative 6x plus 12.
Yep. Alright, and you remember from the graph how this first derivative was a, well, let me go back. First derivative is this one right here. That's a parabola. Yeah? Well, that's a parabola. Right? And then the second derivative, well, that's a line. Right? We're always decreasing by 1 degree, and that's a line. Okay. So, in order to do this, we need to figure out, in order to figure out the intervals that we're going to be testing at, we need to set the second derivative equal to 0. So f double prime of x is equal to 0. So let's do that. Negative 6x plus 12 is equal to 0. You solve for x, you get negative 6x is equal to negative 12, and you get x is equal to 2. At x equals 2,
At this time, high school students are.
We're gonna
listening
pause.
to